So you're following along with your notes, and everyone at home who's watching this is following along with their notes.
It should be.
Yeah,
they're going to get beat up.
Right. If they're not, then maybe they'll, maybe they'll go get their notes out right now. Or maybe they're talking about
Yeah.
So now, let's fill in this blank. Electrochemistry is where we're spending now. And by that we mean the relationship between electricity and
redox reactions.
Awesome. Redox reaction. Reduction and oxidation. And by electricity, what we are really talking about is the movement of electrons. If I can get electrons to move at any speed, in any way, that means I can get an electrical current. And they move a lot easier in metals, and metals make the best conductors. Of course. Right? Because remember what metallic bonds are like? Just a sea of electrons, right? And so they're freely moving from one atom to the other, and that's why metals are better conductors. So we're looking at voltaic cells. And voltaic cells are basically just, here, let's look at this word first. By cell, we mean like a container. Like a beaker, right? Or a cup. So we've got like a container with chemicals in it, right? So what should we put in this one?
I'm feeling energy.
Energy. Okay, that seems like an important part of electricity.
What?
I know.
Get out of here.
Energy that's released in a spontaneous redox reaction is that's used to perform electrical work. And we harness that in voltaic cells.
Of course. Because it's a container.
Yeah, a container of chemicals. Which chemicals? Those that do spontaneous redox reactions.
Of course, spontaneously.
Right, that's the key. So delta G for a spontaneous reaction has got to be negative. Those of you who have already listened to the thermodynamics podcast know spontaneous means the delta G is negative. And a spontaneous reaction just happens on its own, and we don't have to do anything to it to coerce it into reaction. So there's another word for voltaic cells. They're called galvanic cells. And you could use a voltmeter and connect it to your electrodes and see that when the reaction takes place, you actually get an electrical current flow. Really? And you can measure the voltage of that current and describe how much spontaneous it is, like the delta G does. So that's another way of measuring delta G. We're going to work on that. Not this podcast, but next.
Podcast?
Yeah.
Like what are you writing on a pad?
Yeah, nice. Okay, moving on. So the electrons are transferred rather than just from one reactant to the other. They're going to go through an external pathway. And I think we should probably see how this works, because it's hard to just describe. All right, so the metals that we use in our circuit have a special name.
They're called electrodes.
Of course. I think I said that word before, electrodes. That's what we connect our voltmeter to. And metals are good conductors of electricity, so we use those guys for our electrodes. Now we can move on to our big picture of my writing.
A galvanic cell is a spontaneous electrochemical cell in which electricity is produced by means of a spontaneous redox reaction. In this cell, zinc metal will be oxidized and copper 2+ ions will be reduced. To complete the electric circuit, the solutions must be connected by a conducting medium through which the cations and anions can move. This requirement is satisfied by a salt bridge, which in its simplest form is an inverted U-tube containing an inert electrolyte, such as sodium nitrate or potassium chloride, whose ions will not react with other ions in solution or with the electrodes. At the zinc electrode, zinc metal is oxidized, losing 2 electrons to produce zinc 2+ ion. At the copper electrode, copper 2+ ions are reduced, gaining 2 electrons to produce copper metal. Electrons flow from the zinc electrode to the copper electrode. The zinc electrode is dissolving to zinc 2+ ions over time, and copper metal is building up on the copper electrode. Click on one of the buttons to view that portion of the galvanic cell on a microscopic scale.
All right, you told us to click, so I think we should click.
Sounds like a plan.
Okay, Good. Hey, before we do though, I wanted to point out something to you. Notice what we've put in here. Nickel, no so. Why are these guys standard ions? They don't want to react with anything else?
Because they're nickel, no so. Duh.
Right. Because no one wants to hang out with these guys. So we use those ions in our salt bridge because they're not going to be a part of the reaction. They're just going to facilitate the movement of the electron. All right, let's look at the zinc electron.
At the zinc electrode, zinc atoms are losing 2 electrons, forming zinc 2 plus ions, which enter the At the zinc electrode, zinc atoms are losing 2 electrons, forming zinc 2 plus ions, which enter the solution. The 2 electrons lost by zinc metal flow through the wire to the copper electrode. Note that only zinc 2 plus ions are shown in solution. Other ions and water molecules are not shown to focus on the oxidation of zinc metal to zinc 2 plus.
Okay, so we know what was happening at the zinc electrode. Our zinc metal with a 0 oxidation state was reacting with our solution of zinc nitrate so that it was oxidized. Of course, okay? Because it lost electrons. Yeah, we know. Nice stuff. Yeah, loss of electrons is oxidation. Those electrons are going to flow through the wire because wires are good conductors.
You don't use that all.
Yeah, exactly. Let's look at the other electrode.
Electrons formed at the zinc electrode travel to the copper electrode. 2 electrons combine with each copper 2 plus ion in solution to produce copper metal. Note that only copper 2 plus ions are shown in solution. Other ions and water molecules are not shown to focus on the reduction of copper 2 plus to copper metal.
All right, so there's our copper electrode. In this part, we have a solution of copper nitrate. So as the electrons are being added to the copper, notice how this electrode seems to be gaining mass and this one is losing mass. Because the copper ions in this solution are sticking to this copper metal as the electrons are added to them, and it changes it from a copper plus 2 to the copper 0 or element.
Gotcha.
Pretty cool, huh?
I'm pretty impressed right now.
Okay, well, could we just keep this going forever, taking electrons out of here and adding them to there?
No.
Are we going to run out of electrons?
Of course.
So we got to get the electrons back. And that's what our salt bridge is for. We have to have a complete circuit, or we're just not going to get much done. So let's look at the salt bridge.
The salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As the zinc electrode is oxidized to zinc 2 plus, a positive charge builds in the solution due to the zinc 2 plus ions. If this positive charge were not counterbalanced, the galvanic cell would cease to function in a short period of time. The negative nitrate ions flow into the solution containing the zinc electrode, and the positive zinc 2 plus ions move in the opposite direction to balance the charge. For this cell, nitrate ions are chosen because they do not react with other ions in solution or with the electrode.
Yeah, those spectators there, no one wants to hang out with nitrate. We already called that one. Oh, yeah. Okay, let's look at the copper side.
The salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As copper ions in solution are reduced to copper metal, positive ions are removed and a negative charge builds up in the solution. If this negative charge were not counterbalanced, the galvanic cell would cease to function in a short period of time. The positive sodium and positive zinc 2 plus ions flow into the solution containing the copper electrode, and the negative nitrate ions move in the opposite direction to balance the charge. For this cell, sodium ions are chosen because they do not react with other ions in solution or with the electrode.
Great, so that's how a galvanic cell works. And because we can measure the voltage, they're also called voltaic cells. So if a question in your book asks you about a galvanic cell or a voltaic cell, you won't have to be confused. You know, it's the same thing. Of course. Right, so no big deal. Good. This relies on 2 redox reactions, right? But really, it's just one, because the electrons on this side are moving to this side. So it's these 2 solutions reacting with one another that we're concerned about, but they're in 2 different containers. That's why it's called a cell. Remember the container?
The container.
Right. By cell we mean container. I need to get my pen. There it is. Okay, good. Sometimes instead of a salt bridge, you know, that upside down YouTube. It's shaped container.
I thought it was just like an A.
Sometimes instead of that, we just put a porous disc between them. And if you had a Duracell battery, this is what's in there. There's not like a tube of glass inside there. There's just like a ceramic disc that the ions can flow back and forth through that ceramic disc, and they don't have to be contained in two separate batteries, but rather in the same container with a disc between them that keeps each solution separate. Alright. And then suppose that we wanted to drive the reaction in a reverse direction. Then we add electricity to it and force the equilibrium to go in the reverse direction, like exothermic and endothermic, right? Well, if we can make it go backwards, you can recharge your battery. So you plug your cell phone in at night to recharge it because you used it up during the day texting all your friends.
Like Danny?
Like Danny does, like Danny, yeah. She's going to be so glad we talked about that.
I know.
Behind your back.
Pickle or pickle.
Oh dear, I don't know about that. Okay, components of electrochemical cells would be then our electrodes. And there's two different kinds of electrodes. One is called the anode. And this is the metal electrode at which oxidation occurs.
Called it. You even have to look at a piece of paper.
I've been doing this for a while, you know.
Say it's a thug life.
Oh, right. That's what I meant to say. It's
Right.
a thug. Does that make me a thug?
That does make you a thug.
Oh, I think you've called me that before, and I wasn't quite sure if that was good or bad.
It's good.
Okay.
I wouldn't call you anything bad at school.
Well,
Just kidding.
only behind my back.
Of
Like we talked about
course.
Danny.
Oh, yep.
All right, so at the cathode, this is the metal electrode where we have reduction taking place. Sometimes we can get gases to participate as anodes and cathodes, and that seems really weird, right? How would you use a gas for an electrode? But anything that we can get to gain or lose electrons can be an electrode.
Anything.
Anything. So if we had hydrogen gas that gained electrons, as hydrogen tends to do to make hydride, then we could use it for the gaining, the reduction site for a cathode.
Cool.
Right? But hydrogen ions, we know, often form positive charges, right? So they lose electrons easily as well. Right?
So it's probably...
So we could use it for an anode.
Good.
Yeah, it depends on what else is with it. If there's a non-metal with the hydrogen, it will probably lose its electrons. But if we put it together with a metal, we will have to gain electrons.
Gotcha.
Yeah, so we can predict what will happen based on our knowledge of redox reactions. All right, so we need a connection between our two containers that allows for the flow of ions. Remember what we called that upside down YouTube thing?
A salt bridge.
Totally salt bridge, right? And even if we use the porous disc, we still call it a salt bridge. And by salt, we simply mean a metal and a non-metal, a cation and an anion. So we had sodium nitrate in the last example, but it could be potassium chloride, or it could be sodium nitrate or sodium chloride. We wouldn't want to put chlorine in a salt bridge where we had silver, though, or mercury, or lead, because those,
they all are buddies, and then forms.
Right, those would react. But if we had zinc, then we could use chloride, right?
Zinc doesn't even like chlorine.
Right. But we would probably use like the chlorates, the acetates, and the nitrates because no one wants to hang out with them. They're always composed of a strong electrolyte. That's what we were just saying. If it doesn't completely dissociate, it's not good in a salt bridge. And it's got to be something that doesn't produce a precipitate with our three amigos, silver, mercury, and lead. Or with barium, strontium, or calcium. Those guys precipitate a lot too with sulfates. So sulfates would not be a good choice. What's going to migrate toward the anode? Anions go towards the anode. Oh, notice that? Anions, anode.
Oh, what?
See? And so that means going towards the cathode would be
Cation.
no way.
Who would have thought?
It's like they named them that way for a reason.
They don't ever do that in chemistry.
No, we just put random words. Now, since the salt anions go towards the anode, then the electrons are going to go from the anode to the cathode. They're going basically in alphabetical order, A to C, right?
Gotcha.
Electrons go from the anode to the cathode along that little conductor, or normally a wire. So I've got some handy tricks to help you remember that. Okay, they're called mnemonic devices because they're like using sounds to help you remember. Okay, so if you keep your vowels together, you keep your consonants together, then you know anode is anions,
Of course.
and cathode
Cation.
cations. Yeah. So I need to make that for us. We're good. If I can dot my I, that's the hardest. Crossing the T's and dotting the I's. Why is that so hard? Here's another device. You know, McDonald had a farm.
You know he had an ox and some red cats?
Yeah, he had an ox on his farm. E-I-E-I-O. And his cats were red. Yes.
It's a genetic mutation.
Right,
So we do.
right. It's just
Like Clifford,
McDonald's
the big
farm.
red dog.
Oh, I love Clifford.
okay.
I want a dog like that. That'd be cool.
Of course.
So, on McDonald's farm, he had an ox because we know the anode is oxidation. Where did my clicker go? Okay, we're back in business. Anode is oxidation, so an ox.
And ox.
And cathode is reduction, red cats. Of course.
The knee slapper.
That's what I got on my farm too. An ox and red cat.
Oh my God,
And
look at
electrons,
that.
oh, we just said, they flow from A to C in alphabetical order. We got it. This is easy. We could do this. Hold on. No big.
God loves mnemonic device.
Yep. Because we don't want to get mixed up when we're in the middle of an AP exam.
Of course, and you can't even ask the kid next to you because he probably doesn't have the same test.
No kidding. That's nice. All right, well, let's look at standard cell potentials. We use these to determine which metal is considered the cathode and which metal is considered the anode. And I am, oh, right. If it's a voltaic cell, this reaction has to be spontaneous,
Got it.
right? If we have to plug it in and charge it up, it's not spontaneous because we added energy.
That's not fun.
Yeah, well,
That's more words.
it's got to come from somewhere. So, this term, EMF, basically means how do we make the electrons move,
Gotcha.
right? So this motive, like a motor, electromotive force, it has a really weird symbol. So if I draw this weird, am I getting it right?
Yeah, it looks like a C with two
And they go all the way through, right?
Yeah.
This.
and a degree.
So it's kind of like an E, and it has two lines instead.
Of course.
Yeah, for electromotive force. Of course, we use this Greek letter eta.
Eta.
Cool letter. We should always use Greek letters.
Always. I
Right.
don't even know why we even speak American.
We would start your letter with your name with sigma,
Of course.
then have, I don't know what the H symbol is. But you could have alpha in your name
we
and
can just
nu.
throw a whole bunch together.
Yeah,
What's your name?
we'll do it.
We'll do it.
We're going to write your name in Greek.
Like homework.
Oh, yeah, I know what we could do. Instead of homework, we just call it homework.
Ah!
The omega is the symbol for ohms. Since we're doing electricity, we can talk about ohms.
And it makes sense.
How about that? So lame.
I mean,
Science jokes are always
like
lame.
high-five yourself, you know?
Right. Ooh, I'm so funny. All right, these are caused by a difference in potential energy. And pretty much anytime something moves, it's because of a change in potential energy. So let's imagine we've got a hill, and we put a ball at the top of the hill. Why would the ball ever roll down the hill?
Because it's downhill.
Right? So what?
So
is higher up,
Of course.
and it's going to move in such a way that reduces its potential energy. It's not likely to roll in such a way to increase its potential energy.
That is ridiculous.
Yeah. Now, I could show you in physics class when the ball rolls uphill. I could
Really
do that. I know, because that's what they pay the scientists the big bucks for. Make nature do what it wouldn't normally
That's
do.
where you get super crazy ohms, you know?
Right, exactly. But potential energy is going to be converted into other forms of energy when we can reduce the potential energy or have some difference, some change, right? And between the different electrodes, we have different amounts of potential energy. This is what moves the electrons. You can push them from one metal to the other because their potential energy is not the same. Pretty cool, huh? We call this value is cell, and its name is cell potential.
Why did this not come up earlier?
Well, because we just had to look at what the heck was a cell in the first place. So now, cell potential is something we're going to get to calculate. Let's see. Oh, that's what it is. They get my title. Cell potential. Cell potential. Oh, why is it stopping? Because I got a new line next time. All right, so let's make a prediction. Is it going to be positive or negative in this spontaneous reaction?
Positive.
Positive. Because we have a change in kinetic energy that reduces the potential side. We reduce our potential energy, we're increasing the cell energy.
Of course.
Okay, so we're changing it from one thing to another, and one thing goes up, the other one goes down. At least in energy. Okay? Because we know by the law of conservation of energy that whatever energy is lost from one thing has to be gained by another. All right, for non-spontaneous reactions, cell potential is negative. Just like, no, not just like delta G. Opposite of delta G. Delta G is negative for spontaneous.
Of course.
Yeah, just to confuse us and make our lives tough.
They had to go and be nice and like make everything relate.
Yeah, I know. Trying to keep track of chemistry and remember everything you've ever learned about it.
I'll just go get tattoos of this.
Yeah, Shannon keeps thinking of all her tattoos she needs to get for her chemistry exam. All right, well, here's our factors that are going to influence cell potential. We're going to have to consider what reaction is taking place, right? Which metal is it, the zinc or the copper, or whatever else there could be. We have to consider the concentration of the solutions, which we measure in molarity. Molarity, just as a reminder, is moles per liter.
Of course.
And so if we had like more particles in the solution, we probably have more potential.
Well, there you go.
Make sense?
Yeah.
And then the temperature is going to be a factor. Just like with any other reaction, if we heat it up, it goes faster. So electrochemistry is no different. I think we're done with this slide. Nope, I was wrong.
That was a lie.
Yep, I was just kidding. So the cell potential, it's about this little circle thing here. Remember in Gibbs free energy, when we put a circle here, that meant something specific. And for S and for H, that little circle has meaning for us. It means that we are at standard conditions.
Of course.
Right, and standard conditions for STP are not the same as standard conditions for the rest of chemistry, because no one wants to do a reaction at 0 degrees Celsius.
That's ridiculous.
I know, you'd have to wear a stocking hat and mittens and all kinds of stuff. In the chemistry lab, that wouldn't work.
That'd be cute.
And all your water would be frozen, so it'd be hard to get these reactions.
Of course.
Yeah. So standard conditions in chemistry, unless it's gas laws, it's going to be 25 degrees Celsius at a concentration of 1 molar and a pressure of 1 atmosphere. Those are our standard conditions.
Or 760 millimeters mercury.
Oh, ooh. And the kilopascals?
Of course. It's just
101.8.
Yeah, exactly.
I saw you.
This is why it's on the sheet.
Right, right. So anytime you see this little circle next to a symbol, that means we're at standard conditions.
Of course.
And they're going to assume you know this, so they won't tell you the concentration when the circle's there. What's the concentration?
Standard condition.
Right, 1 molar, because it's standard condition.
I thought.
Wow, it turned blue. I don't know what fancy stuff I did there, but hey, I like it. Let's move on. So if we have an EMF, an electromotive force, then we can use that to determine what will happen in our chemical equation. We can tell if it's going to be spontaneous or non-spontaneous. So the more positive your standard reduction value is for that half reaction, the greater the tendency for the reactant in that half reaction to be reduced, thus exceeding reduction. Okay? And when you did the practice test for the AP Chem exam for your spring break assignment, then you saw a table full of values with, it says standard reduction table. That's what this means. It means how easy is it to reduce this particular substance.
I couldn't just write a definition.
Well, now you know.
Give me a hands up.
Yeah. And if something is easier to reduce, then that means it's a good oxidizer. Yeah,
of course.
Remember oxidizing agent and reducing agent? Well, now if you look at that table and compare two different things, you can tell which one is your oxidizer and which is the reducer, because the one with a higher number, the more positive it is, then the better it is to act as an oxidizing agent.
Good.
Yeah, so we can tell what's going to happen. And the half reaction that has
The smallest.
the smallest or most negative is the most easily reversed. So we could get that one to be oxidized easier. The other one's reduced.
Gotcha.
Okay, so our standard table of reductions is used as an activity series. They don't have to tell you which metal is more active, because now you can figure it out. Which one's going to turn into a metal or replace another one, you can read it from the table.
Good.
And that will always be provided for you. I haven't given you that very often on your AP Chem exam, but you didn't know what to do with it. Don't know.
Good.
I know, until our very last unit of the
Right.
semester.
Sweet.
Yep, here we are. We're going to use that reduction table. And if you don't have a reduction table, you'll find them in the appendix in the back of your book. So you should go read your book right now, first part. Yep, we've got one in the classroom. Yep. So the potential associated with each electrode describes the ability for what? Reduction or oxidation?
Reduction.
Right, this is the reduction table. So it's the ability for reduction to occur at that electrode versus method. Okay, and you found Appendix E on page 1128. It's right before Bob.
Good, yeah.
The answer's in the back of the
Of
book.
course.
Okay, good. So we're going to look at metals, but what they do to get these numbers is they compare the metals to the hydrogen electrode. So hydrogen is the one we say is going to be our standard that we compare everything else to.
Good.
When you do your lab, we'll use zinc as our standard to compare all your other values. Because zinc is pretty well known and well established, very consistent. So that will be our standard now. You always have to have a control in your experiment. Or it's not a good experiment. Well, in the past, when we do the change of something, we're really measuring the change in potential energy, right? And for change in heat, we did the heat of the products, minus the heat of the reactant. Remember Hess's law?
Of course.
Right? And then we did the same thing for entropy, products minus reactants, and for Gibbs free energy too, products minus reactants. Well, guess what?
Products minus reactants.
Yeah, it's the cathode minus the anode for a galvanic cell every single time. So if you can figure out which one's your cathode and which one is your anode, then you take the potential from your little chart thing and you read it on your chart, cathode minus the anode, and you're done calculating.
Good.
Yep. So for any two metals that we could choose, we can calculate their cell potential. So if the stoichiometry of the reaction changes, where now we have two electrons and I don't know, we have 2 coppers and 1 aluminum zinc. Guess what? You don't change it. Do not multiply the values for that metal. It's already been factored in when we compare them to the standard hydrogen electrode. It's already included in that reduction table. So we're not going to mess with stoichiometry. So now, if we have a more positive reduction potential for a metal, then we're going to use that as, which one, the cathode or the anode? Cathode. Right. Of course. So the metal with the larger reduction is the better cathode. That's what you just said. Oh, but wait, we said that works for a galvanic cell.
No, voltaic and galvanic, same thing.
Right. So you won't let me trick you on that?
Not anymore.
Right. Oh, my writing. So writing. All right, here's an example of the type of calculation we might be asked to do. So we have these 2 half cells for our voltaic cells. So in one container we have metal, cadmium, and in our other container we have our metal, and so we have these 2 metals, and we want to figure out what's the voltage. So here's what we do. Check it out. We're going to start with writing a reaction. So cadmium, if you find it on your table, it tells you what it's going to turn into. It goes from a 2+ to just the metal, and elements have a 0 oxidation state, right? And in your table, you look up this value for cadmium? Yep. Good, I'm so glad you're checking my work. Because I do from time to time make mistakes. Here it goes. It's happened before.
There's no way.
All right, and then 10 goes from a 2+ to a 0. There's a chance it could go to a 4+.
Yes.
But that's not the one that we have written down here. Look, it says 2+, so let's not do the 4+. Let's just do the 2+.
In the trash.
We'll do what it says to do.
Of course.
2+. Okay, so which one is more positive? Which of these 2 values would you consider to be more positive or closer to 0?
The 10 one.
The 10 one is closer to 0 because if you were on a number line, the 0.1 is closer to 0 than 0.4.
They're all really close to 0.
Right, they are. So we have like a number line that increases by 10.
That's awesome.
Yeah. So our cathode is going to be the 10 because that's most positive. The cathode and the anode. So at the anode, notice I flipped this reaction around because your reduction table only shows reduction, but the anode is oxidized. So we have to flip this around because the reverse of reduction is oxidation. So we're going to take the cathode minus the anode, and watch your signs here. When you do this, it's going to be a negative number minus a negative number.
So it's positive.
Well, we're adding. It depends on the size of this negative number, whether it's positive or not. But in this case, we get a positive voltage.
That's good.
Yep, 0.267. So if we had a 1 molar solution with cadmium and a 1 molar solution with tin, and it's at 25 degrees Celsius and a pressure of 101.3 kilopascal, we would expect our voltage to be 0.267 volts.
Of course.
Right, and then in real life, when Shannon does this experiment, she's not going to ever get 0.267 exactly. Is it because you're that chemist?
Of course, no.
No, silly. Shannon's a great laboratory chemist.
Only when I'm with Danny, and we have those cells.
Yeah, you guys did really well with that lab. But really, there's random error that's beyond your control.
Oh,
You can do everything right and still not get exactly what you're expecting. Yes. So now let's do another one. Only this reaction doesn't quite look like the other one.
Of course not.
Yeah. Well, let's figure out what's going on here. Because I have lead oxide now. Sodium metal has a 0 charge. And the lead oxide adds up to 0. But now we have oxygen with 2 of those bad boys. So we know what kind of lead is this.
We know that this lead is 4.
Yeah.
Good.
And you're so good at classical naming. we call this?
Perfect.
Yeah.
Good. One up.
And then the plummet ion turns into the plumbless ion in this reaction. So I believe I already typed out our half reaction. Oh, well, isn't that? Okay. There's one half reaction, sodium becomes sodium ions, and then the lead 4 becomes the lead 2. Is that also reduction to go from 4 to 2? That gain of electrons or loss of electrons?
Lots of electrons.
Let's see.
Gain of
Let's see, what would make us less positive?
gaining electrons.
Right, gaining electrons. So these are both reductions. Both reductions. We can't have a redox reaction where they're both reduced. We have to decide which one is going to be our better reducer. Which one is more positive?
Sodium.
Yeah, that one's easy.
Of course.
Yeah. When they're negative numbers, you got to think a little harder, but not this time. Oh,
Do not multiply, Dustin.
Right. We have 2 of these. We're not going to multiply the reduction by 2. And we have, the complete redox reaction. That's what we're doing here. We started with these half reactions. So we know we lost 2 electrons because we have to balance out with our lead.
Of course.
Yeah. All right. And then we have to add enough waters to balance the oxygen.
Of course.
And then we had 2 waters, so that means we've added 4 hydrogen ions. So that we can have a complete redox reaction. How's that look to you?
Looks perfect.
Yeah? Good.
Good.
So, what do we do with this? The overall potential is going to be cathode minus anode or anode minus cathode? What did we say before?
Cathode minus anode.
Is it going to always be that way?
Yes, of course.
Definitely. Cathode minus anode. For a galvanic cell, it's always the cathode minus the anode. So we take the cathode, and I added my anode. Why did I add it? Because we can't have 2 reductions at the same time. And this is reduction. We want to go backwards, right? Because this was not our reducer. The other one's a better reducer. So this is going to be an oxidizer, and we have to reverse it.
So instead of a positive 1.5, it's a negative. Oh my goodness.
Yep.
All of a sudden.
I know.
Like a bus.
There you go. Hey, look, we're done. This is the end of our podcast. We're going to practice this more in class with your classmates there to support you. And I'll be there too.